Okay, everyone, this is the final talk of today's workshop and event. We will be hearing from Lukas this time. David was technically revoked there last time. So Lukas today is going to talk to you guys about quantum device architecture for low overhead quantum architecture. He is also part of the Will Oliver Lab or QS at MIT, and previously he was at ETH Zurich before he joined MIT. This will be the last talk. After this, we still have the technically breakout sessions where Eli will then explain sort of a little bit what we're going to do. And then we will later, obviously, see each other tomorrow again, where we'll have NVIDIA in the morning for 3 hours. Sounds long, but the first hour is really just an overview talk. And then the rest is where you guys will actually code, and all of you, so beginner and advanced. Again, maybe just reminders, all the forms we've sent them to you via the emails. So for questions tomorrow for the panel discussion, as well as for feedback, right? We really appreciate if you pull those out. And without further ado, let's give it up to Lukas.
Right, amazing. So yeah, I'm excited to give sort of the last talk in the advanced track of the sort of formal workshop. I think this is actually a nice sort of cap to everything that we've learned, or a follow-up of everything we've learned. We've so far looked at how to design devices, all the techniques that go into maybe ABCD formalism or EM solvers. But there's a lurking question, which is what kind of devices do we want to build? And this is essentially the question that I want to answer with this talk. The thesis is that quantum error correction dictates the architecture that we choose for our devices. And so to do device design, I think that we designers need at least some level of understanding of quantum error correction. So for those of you who are not familiar, what is quantum error correction? Well, in essence, there's this diagram of error rates, or qubit error rates. Physical qubits typically have error rates 10 to the minus 2 if you're good, or 3 if you're really good. But we can't really push error rates much below that, like just by improving the fab or coming up with better qubits. There's a natural limit to that. The only problem is that to run useful computation, we need to get to sort of the 10 to the minus 9 up to 10 to the minus 12 level. And that's like a huge chasm right there in between those two regimes. And error correction is essentially the answer of how we bridge this gap. It's sort of the idea of how we can get arbitrarily low error rates by trading in the sort of number of physical qubits for the fidelity of logical qubits. And we'll learn about sort of in a high-level intuitive way how it works. Right. And just to give you another motivation, I'll peek into the industry IBM quantum roadmap. You can see that their sort of near-term goal that they're working on, 2025, here includes a device that has non-local coupling. They want to do logical memory, and even also their long-term goal sort of has error correction built into the roadmap. Going over to Google, you see sort of the same picture where error correction dictates every single step of the roadmap. Every single device is built from start to end with error correction in mind. It is the only way that we are scaling these devices, and it sort of top, bottom tells you what kind of device we want to build. Both near and long-term devices are designed for error corrections, and so to get the architecture right, let's get a base level understanding. Now, these are like big companies, and you might be thinking, well, we're academic researchers, what do we care about error correction? And you're right, there's a lot of interesting research that doesn't involve error correction, but even small academic projects, this is sort of what David and I are working on. It's a 9-qubit chip. It's already mid to large scale, but it's sort of manageable for an academic lab. This is an error correction project. To know what kind of device you have to design, you have to get the error correction right first. And this is a small code that where we can do interesting operations on and study sort of some questions. And for that, a base level of error correction is required. All right. So before we dive in, I want to give you like a basic rundown of the history of error correction. There's like two codes or two families of codes that I'm going to focus on. This first one being surface codes. You've maybe heard of this one before. It was introduced in 1997 by sort of this foundational paper of Alexei Kitaev, where he introduced the surface code in its earliest form. We then had further work where we established sort of the level of physical qubits fidelity that is needed to even make this code work. And that was surprisingly forgiving. How we figured out how to do computation with the surface code. And Then most recently, sort of last year, Google demonstrated the surface code actually working in practice. And again, they built a lattice that they scaled, and they showed that surface codes actually protect your quantum information as you make them bigger. And then I'll look into a very different kind of error correction, these so-called quantum low-density parity check codes. That's a mouthful. We abbreviate them as QLDPC, still a mouthful. It's a different parallel track to the surface code. The idea is we can get maybe more efficient error correction if we have slightly different codes. And it was kickstarted in 2013 by Daniel Gottesman, who said that you can use QLDPC codes in principle, this existence proof, to get quantum error correction to work much more efficiently with much fewer physical qubits. And then 2022, we had explicit constructions of actually how to build these codes, but they were not practical yet. And then that's what IBM did in 2023. They put out a paper where they said, oh, I have a code that doesn't look too different from a surface code. If you sort of put your designer's goggles on, this is a base layer that is weight 4 nearest neighbor connectivity, but there's sort of one difference, namely you have long-range couplers. I want us to understand where these long-range couplers come from so we designers can appreciate the challenges that come from going to this next level of error correction. And then even very surprisingly and very recent, just last week, we had a demonstration of sort of a small version of this code by a group in China where they actually built this using superconducting qubits. And I'll talk a bit about that on a high level, how they resolve the crossings using air bridges and long-range couplers. We'll touch on that a bit. And so comparing the surface code against this bivariate bicycle code, if you run the numbers, the surface code has about a surface code of distance 13. That's like a medium-sized surface code. Takes about 337 qubits to build. It has one logical qubit that's quite protected. The distance 12 bivariate bicycle code is sort of the most comparable code of this family. Takes similar number of qubits to build, but it has 11 logical qubits. And so if you want to sort of size up the surface code to compare against that, you see that we have about a number of physical qubits that is 10 times higher than the bivariate bicycle code. So the motivation to going to this more complicated connectivity that then we have to deal with and how to design that is exactly this number down here. It's a 10-time more forgiving size. So you get up to 10x qubit savings, but there's no free lunch. You trade in non-local connectivity, which is sort of this interesting hardware design problem that we need to deal with. All right, so we'll talk about a couple things today. I've divided it into 3 parts. There's going to be a minimal and very visual intro into how quantum error correction actually works. I'll then go into how we get to the surface code and how we get to the bivariate bicycle code, their connectivity, and I'm going to work as much as I can with just pictures and colors. And the last part, we're going to briefly touch on what the implications are for device architecture and the components we need to design, the type of devices we need to be able to build. And again, please ask away, ask questions if you have any. This is something that's a bit more out there. It's QI, it's maybe not what we're used to, so feel free to ask and interrupt at any point. Also online. So let's start with a very simple example. Yes?
What kind of metrics are there for RAM size for quantum error correction?
For RAM size?
Yeah, RAM.
Oh, I mean, that's sort of getting at a very high level of computer architecture, quantum computer architecture. I don't think as far yet. I don't think people are thinking as far into the future yet. The basic answer, what people are thinking about right now, is they're just making a large surface code and then many, many surface codes. It's going to be a large 2D plane, and we just count the number of qubits. So we're not going to RAM yet. We're just at sort of qubit registers, logical qubit registers. All right. There's no other questions. I'll just dive in. How do we protect information? Let's start with classical error correction. A single bit. That already encodes some information, right? We use 3 parameters. This is some jargon we need to introduce, but we're not going to introduce much more than this, I promise. N, K, and D are 3 parameters. That's like a snapshot summary of your error correction code. N is the number of sort of data bits. K is the number of logical bits that are actually encoded in those N bits. And D is the weight of the smallest undetectable error. Sort of the larger the D, the more protected your information. So in this code here, you have one data bit, you have one logical bit encoded into it, but already a single flip will corrupt the information, and there's no way for us to tell whether the bit flipped or not. There's no operation we're running to check against this. There's a question over here?
No, yeah, quick one. The last few slides you were calling it physical.
Sorry, physical versus logical? Oh, yeah, that's a very good question. Yeah, so that's actually on the next slide, or on this page here. If we build up a slightly larger code made up of 3 data bits, we can add something called check bits. Both of these bits are physical bits, but they play different roles. The squares are check bits. They don't hold the information that we want to protect. They are used to check for errors. And the data bits, they take the role of holding the actual information that we want to protect. And so together, they are actually the number of physical bits. So the number of physical bits that are in your code overall is roughly 2 times n, because you have about as many data bits as check bits. So going forward, I'll just write them as squares and circles. But remember, squares are checking for errors. The data is holding the information. All right, then we actually connect them up. And by connecting, we sort of can check for errors that happen on the data bits that any check bit is connected to. Now, what I want to show here is I've added 3 checks. But you can believe me that sort of this top check is actually a linear, sort of is a redundant check. It encodes exactly the same information that I already have with the lower 2 checks. And so we can actually leave that one out. We're already touching every single data bit with a check, so every bit is already protected. No need to add more checks to it. That would be redundant. And then we can run the same parameters. N, the number of data bits, is 3. K is actually the number of logical bits. How do we determine that? There's a very simple trick, very simple formula. N, number of data bits, you can think of that as spanning degrees of freedom. The more data bits you add, the more degrees of freedom you have. The checks are like constraints on your degrees of freedom. And so the resulting degrees of freedom you have is the data bits minus the independent check bits. And so that gives you one logical bit that's encoded here. And then what's the distance? Well, if we add one flip, this check lights up. And it tells us an error occurred, so we can catch this error. This one doesn't corrupt our information. A second flip, I want to draw your attention to what happens here. This is really important. 2 flips are acting on this one check. And the check is only able to measure parities. And so because it's measuring sort of 2 flips to its neighbors, the resulting parity is again 0. It is not able to actually measure that an error had occurred. This is how these checks work. But luckily, this other check bit is still able to catch the error. If you now add a third flip, both checks remain in the 0 state, and we don't detect this error, setting the distance of this code to 3. This is really important, so if you don't understand, ask away.
About error data.
Yeah.
About errors in the check.
Very, very good. In this presentation, we won't talk about that, but the way you solve the errors in the check is by actually repeating the measurement again. So if you repeat the measurement again, and there was an error before, now you've reset the error, it would have to occur again. The error would have to occur on the check bit again for you to get the same wrong result out. And then you majority vote out in sort of the time dimension. Yeah, it's a good question. Flag qubits are another way, but that's sort of already getting into the details. So we won't talk about that here, but it's another way to make errors in the checks sort of more resistant. Yeah. All right. Let me give you a slightly beefed up example. It's the 7-bit Hamming code. There was a question online.
What about the 11?
Okay, I don't know what that is. 7-bit Hamming code, very similar principle. We just sort of connect it up in any way. There's 7 data bits, and there's 3 check bits. So the math again, 7 minus 4, we can do that. 3 degrees of freedom that are in this code. Every bit is touched by at least one check. And so if we insert some errors here, flip that bit, We can see errors light up. All right, you flip another one, now all three are lighting up. But if I flip a third one, I can reset them all to 0. So 3 errors suffice to go undetected. That sets the distance of this code to 3. So this is how this works. NKD really describes the size of your code, how many logical bits you have, and the level of protection.
What about the case that you won't be able to tell which, but we found that somewhere? Where the first.
So that's the problem of decoding. So what you do is you look at sort of these patterns of bits here, and you try to use these guys to guess, well, what data bit may be flipped such that I get this syndrome pattern out. And you're right that that's not a one-to-one mapping, and it's actually a really hard problem. It's an NP-hard problem that we need to solve in real time. So it's not fun, but people are starting companies to solve it. So we might get there. We won't touch too much on that here, but it's a good point that you're raising. We actually need to infer the error location to correct for it, and that's a non-trivial process. All right. So that's classical error correction. Quantum error correction. We have 2 types of errors. You know, a qubit, it's defined on a block sphere. We all know the story. There's bit flips, but there's also phase flips. There's an azimuthal angle and there's a polar angle. The bit flip is an X sort of flip that changes your 1 to 0, and the phase flip is like a Z rotation that creates a phase. But for us, we just need to care about the color and the letter. That's all we care about here, or even just the color. So you might be wondering, how do we protect against these types of qubit errors? Well, you can use anti-commutation. That's the core principle. We don't need to get into the exact mechanics of how this works, but X and Z anti-commute. That's just quantum mechanics at its core. And we can use this anti-commutation to actually measure parities much the same way. So let me explain the rules of the game. If we beef up these, if we promote these bits to qubits, now they're all qubits, and an error, X error occurs on this data qubit, well, then you can basically do the same game where if the colors are different, so red, an error, is different from green, it anti-commutes, and so that's why this check gives you a 1. This check also gives you a 1. But this check is a 0 because there's no error that it's sort of measuring. If we add another check here, this one does light up, but this check is being touched by two X errors. And again, the parity is 0, so the check bit doesn't register an error. There's reasons as to why these rules are like this. We won't be able to get into that because our focus is to understand the device architecture. But these are the rules of the game, and they're actually very simple if you break it down to this. Now, this is only correcting for one type of error. To correct against both types of errors, and therefore all types of quantum errors, we need to add a second parity check sort of construction. And in this time, in the other basis. So if we add errors that we had before, that doesn't light up at the top because the colors are the same. But if we have a Z error, the colors green and red are different at the top here. It means that these checks are checking for anti-commuting errors, and they light up. And so the rules are much the same, that Z errors are checked by X checks, while X checks, are detected by Z checks. And so you can visually reason about these codes. A Y check, you might be wondering, and we need Y checks, or a Y error. Y error can be decomposed into an X and a Z error, so this will just flip both types of check. And so taken together, using X and Z checks, we can detect for any error in our code. The last thing I want to point out is that these checks, they need to commute so that the code is actually functional. That means they need to overlap in an even amount of places. And we can actually confirm that in this mess of lines, every pair of checks only touches on 2 or an even number of data qubits. All right, what kind of code is this? This is the Steen code. It has parameters 7, 1, 3. How do we know this? We can count the number of checks. We have 6 checks now, so that's 7 minus 6 is 1 logical qubit that we're encoding. And again, there's 3 errors I can insert that already go undetected. So that's basically all the formulas I want to show. I know that's already a lot, but these are the rules of quantum error correction. And with that, we can go to a very visual reasoning of the surface code, of the LDPC codes, and that's what we'll go into next. If there's questions, this is a great opportunity for that. All right. So let's talk about the surface code. The first thing we do, oh yeah. No, there's no, yeah. Yeah.
Might be a 1, might be a 0.
Yeah. That's a very good question. I'm guessing the question is like these errors, they could be a superposition of X and Z, for example. Yeah. So an error, you can think of, it can be an arbitrary superposition of X and Z, but actually by performing a measurement, you're projecting the error from some superposition of maybe a no error, X error, Z error, or Y error. You're projecting that superposition into one possible scenario. So the measurement actually discretizes the error. And then because you perform this measurement and the error is discrete, this analysis sort of holds. So just take away that measurements discretize the errors. The state isn't discretized or collapsed because you're not measuring out the individual data qubits. You're performing multi-body checks. But the errors are projected.
Measuring some kind of symmetry.
Yes, exactly. You're still in a protected subspace. You're not learning about what state you're in. That's why you're not collapsing the state, but you're learning whether you were outside of the subspace or not. And you're projecting the error to a discrete error.
Like an algorithm, any algorithm would work.
Yeah.
Or
yeah.
Only some subsets of
no, the logical qubit itself sort of has, you have access to sort of the same virtual Hilbert space, but it's a logical one. It's spanned by multiple physical qubits. But then on the high level, you can sort of just abstract and say it's a logical qubit that has access to the entire Hilbert space. There's nothing that's hidden or forbidden in that region. Yeah, that's a good question. Some of those details where we unfortunately don't have enough time to go into a lot of depth, but I want to talk about device architecture. So let's dive in. Let's tile the plane with sort of data qubits and check qubits. Makes kind of sense. And now we can draw our connectivity just by adding lines between the qubits. And this gets quite messy. So let me simplify this by creating these tiles. They imply the connectivity. So if you see a tile, you know that this is sort of what's implied. And I can even remove the checks. And now the tiles imply sort of the existence of a check qubit and the connections there. So if I draw this, anyone guess sort of what the connectivity is? It's a check qubit connected to the data qubits. I think that's simple. Here too. Now, tricky one here. I'm drawing tiles also on more distant qubits. This implies long-range connectivity, but the rule is pretty much the same. It's a check over 6 qubits. 4 of them are nearest neighbors, 2 of them far away. There's no reason why I can't do that. All right, now to the surface code. The first thing you do is you tile an infinite plane. For us, that probably doesn't make any sense, but we're just putting an infinite amount of qubits across the plane. And doing this, we can get a very clean sort of analysis of what's going on. Let's insert a check. If now you have an error on this data qubit, the check will light up. If it's a Z error, though, it won't, because those commute. They just go by undetected. So let's add a neighboring check in a different basis. They only overlap on an even number of data qubits, so the checks commute. But this check here will anti-commute with the error and we'll be able to catch it. But what happens if I have a second error here? Well, again, then this check is touching an even number of errors and it won't detect it. So we keep sort of tiling this plane. But what you see is that if I make the error chain longer, I always need to add, then the errors might go undetected. Also in the other bases, I can sort of play this game. If I go all the way across, none of the errors lights up and none of the checks light up because they all are touched twice by an anti-commuting error. But I can I can beat it. I can make the plane larger, and then I can still detect these checks. But if then the error chain is again longer, I might need to make the plane even bigger. So in the infinite plane, you can sort of get this very crude argument where in the infinite plane, you'd have to have an error chain that is infinitely long. So all sort of finite sized errors are suppressed in this infinite plane. And we also get an idea of what the connectivity is in this setting. Specifically, in the infinite plane, we can also confirm that, as we make the code larger and larger and larger, the distance of the code, the distance of these errors, they need to increase. And we also know how to translate this to a connectivity. Let's just wait for nearest neighbor. That's actually quite easy. This is the bulk connectivity of your code. The building blocks of the service code are these wait for checks. And to get the bulk behavior, we're looking at this infinite plane. But obviously, we can't build infinitely many qubits, so that's not what we're going to do. Instead, we'll try to make a finite-sized plane. What's the easiest way to close a plane like this? The easiest way is actually to wrap around the left boundary all the way to the right boundary, and the top to the bottom. Anyone know what kind of shape you get? It's a donut, or a torus, maybe is the better word. So this is the shape that you get out by sort of just wrapping around the infinite plane. And it's essentially the cleanest and simplest way to make a finite-sized infinite plane. What does it mean? Obviously, no one's going to build a donut-shaped chip. So that's not what we're going to do. Instead, let's look at what this looks like in a simple, small-scale example. These are like 18 data qubits. And now these checks, they basically do these same wait for checks in the bulk. But along the boundary, you have these long-range periodic boundaries that go around. Also the X checks, they also go around. So you end up with something like this. It's the toric code. This is the same sort of donut, but maybe it's more digestible. You're like, maybe I could build it, but maybe that's a bad idea. What's interesting is, although the service code is basically a nearest neighbor code, right? We saw that in the infinite plane, it's just nearest neighbor. But like this toroidal embedding creates these long-range boundary connections. It's actually kind of annoying because it's not what the code really is. It's just the embedding that creates this long-range boundary. But hey, that's sort of the rules of the game. We'll get to how to fix that, but let's analyze this code first. The parameter is 1823. You can believe me that there's 16 independent checks in this code. So 18 minus 16 is 2. We have 2 logical qubits. And if you like insert some errors here, you can see that 2 errors are still being caught, but 3 errors in one row, they don't light up any checks. And so this goes undetected. The distance of the code is 3. That's the level of protection you have. Also in the other bases. But we're not really happy. There's something doesn't feel right with this code, right? It's kind of weird. There's actually a trick. Let's just get rid of the boundary, right? We don't need it. So let's just delete the checks along the bottom and the right edge. And we get something like this. Feels much better, right? What kind of code is this? Well, this is actually the planar surface code, the smallest distance 3 planar surface code. Turns out you can do it. You can do what we just did. And the connectivity and the checks that you get, they look something like this, just like expected, just as expected. Let's go through the parameters. There's 13 data qubits now. There's 12 checks. 13 minus 12 is 1. Someone notice what happened? We lost a logical qubit. So again, there's no free lunch. We made it planar, but we kind of halved the number of qubits. But maybe that's the trade we're willing to make because now it's planar code. So again, we no longer require the long-range boundary connectivity, and it's nice that we can actually get this property back of the infinite plane. The actual code, the bulk connectivity of the code is planar. So there should be a way to get the code to be planar in reality as well. And that is possible, but the trade-off is you lose a logical qubit. But sigh of relief, we don't need to make long-range periodic boundaries or build real-life donuts. If we insert errors, we can trace back the distance of the code. Let's go sort of on this diagonal. 4 data qubits are still lighting up, and we still get an error. 5 connecting the top left and the bottom right lead to an undetectable error. You might think, okay, why isn't the distance 5? Well, it turns out there's a smaller path you can take that is only require 3 errors so that every green sort of check is touched twice and not flipped. So the distance of the code is actually 3, although there are also some paths that are distance 5. And some people, they use this intuition that, this might not be the most efficient planar version of the surface code. And they said, what if we sort of just flip it on the side by 45 degrees and then get rid of these boundaries, these weird data qubits on the boundary? Then these 3 errors are still limiting your code. They're still undetectable. In this drawing, though, of the code, already 1 error will go undetected because green is the same color as the check. And so that commutes and goes undetected. And so the reason why I'm drawing this is because they then realize, well, we need to add at least some checks around this simple surface to catch these weight 1 errors. You need to choose an appropriate boundary. That's not easy. So when you're cutting up like a large code, you're cutting up a torus, you need to choose the right boundary. Otherwise, you have like these weight 1 errors or low weight errors that will corrupt your code already. And this is what is known as the surface code, the rotated surface code. This is the gold standard of quantum error correction today. We've like at least visually derived where it comes from, starting from the torus, cutting it up and rotating it. This is what you get. It has 9 data qubits, 8 independent checks. So we still have 1 logical qubit, and the distance of the code is still 3. So this is actually just better than the unrotated version. So again, whenever you see a code, ask, is it cut up? Is it planar? Is it rotated? Because only then am I going to build it for you.
A very general question online. What different, I guess, modalities, like quantum computing modalities, like SC2 versus atoms, would they use different classes of QEC codes, or like in general, do they implement them differently? Like, does it change?
Yeah, that's a very good question. It ties well into the sort of theme of the talk. Depending on the code, you might need different types of connectivity. Neutral atoms where you can move qubits around, they might be more prone to doing something like periodic boundaries because they can just move the boundary toward each other. For us, the qubits are stationary, so we prefer a rotated surface code much more. There's other nuances that tie into this discussion, but I would say the connectivity of the code goes hand in hand with the platform and the architecture you choose to implement it. And I think there are both strengths and weaknesses to superconducting qubits, but overall, I'd say it's a quite potent platform to also build out some of the non-local codes that we're going to see. And I'm going to show some experimental demo from the Chinese group in a second. All right, so rotating the qubit lattice reduces the number of physical qubits. That's a key takeaway. And the connectivity, if you just draw out the connectivity, this now looks very familiar. If you've seen Andreas Wallerhoff's talks like on Monday, you might have come across this connectivity and might have wondered, that's a very weird shape. Like, why are the lines so zigzaggy? Why is there like a spiky boundary? Now we know where that comes from. It's essentially to get the smallest distance 3 surface code. This is an experimental device, a chip that has exactly the connectivity we just derived. And we can now understand the hardware requirements. Why are there 17 qubits? Well, the answer is 9 minus 8 is 1. We want 1 logical qubit. That's why there's 17 qubits. That's why it's an odd number. Why is there weight 4 connectivity? Well, that's just the stabilizers for the check tile for the surface code to catch all errors. Why is there a spiky boundary? Well, we rotated the surface code and we cut up the boundary. That's why there's a spiky boundary. So now there's at least some intuition behind why it looks the way it looks and why it's sort of kind of funny. But the exciting thing is people have built this. ETH was the first to demonstrate a distance 3 surface code. And then Google followed that up with scaling a surface code from distance 3 to 5 to 7 and showing that the logical qubit that was encoded just kept getting better and better, actually exponentially. They improved by a factor of 2. The error rate went down every time they increased the distance. So that's already exciting. You're seeing these exponential improvements. You're going from 10 to the minus 2 to 10 to the minus 2, and maybe one day to 10 to the minus 9. And so, yeah, this is real life science that's happening, and it's quite exciting to see theory from error correction to be implemented in hardware. But you came to this talk maybe to talk, not to hear about the surface code, at least now we know it, but to hear about low overhead quantum error correction. That's what I put in the title. So let's talk about that. Let's go back to these QLDPC codes and ask ourselves, how are they constructed? And what are the kind of intricacies of that world of codes? So let's start off with the rotated surface code. It's a good place to start. If you look at this formula over here, the observant eye might spot something. N minus the number of independent checks, that's your K. So what's one way to increase the number of logical qubits without increasing N? Anybody know? Reduce the checks. So let's do that. Let's go ahead and delete an error, delete a check. Which check do you want me to delete? Maybe the top right. Okay, amazing. We deleted the green check on the top right. And in fact, it is correct that now 9 minus 7 equals 2. Crazy, right? And so you have 2 logical qubits stored in this code. You just increase the surface code to a QLDPC code. But there's one problem. This wait 1 error will not be detected. So yeah, not great. You can do something about it. Let's check for that data qubit, but without adding another check back in, what's one way to do that? Someone have an idea? Well, if you remove that qubit, you're making n smaller by 1. Then 8 minus 7 is back to 1, right? So connect it to another check. That's a very good idea. We can do that. Now, a wait 1 error here will be checked by this one, right? So that's kind of great. But what did I tell you? Someone see what the problem was with this code. What did I tell you about how the checks need to be with respect to each other? What property do they need to have? They need to commute. Do these checks commute? Can we verify whether this green check and this red check commute? They're touching on an odd number of data qubits. So the answer is no, they don't. So unfortunately, our trick didn't work. But somebody know, this is the last question I'll ask, how we can fix this. We can, what was that? You're saying we can, to a different check? Maybe there's a way of doing that. In this way, I want to resolve the anti-commutation between these 2 checks. So we might need to add something to restore an even number of sort of data qubits that they overlap on. Kind of a tricky question. This one here? Or connection. Yeah, exactly. That's very good. 100 points. You can add another connection. Essentially, that's the idea. And now, again, you've restored an even number of overlaps between the green and the red, and they commute, and we catch the error. So that's great. Only caveat is like 2 errors in this case will still touch this check, the green check, twice. So the distance is only 2. But I just want to convey the idea that what we did here, we deleted a check, we added long-range connections, we increased the weight slightly. The connectivity that we get in the end is something like this. And though we didn't quite make the next world-changing code, at least we increased the number of logical qubits without the distance dropping too far. And how did we do that? Slightly higher weight, non-local checks. That's the takeaway. QLDPC codes have slightly higher weight, non-local checks, and that's how they increase the number of logical qubits. It's by getting this difference to be net positive as you grow the code without tanking your distance. But there's more formal constructions that give you a good code that actually performs well, where the distance also stays high and increases, and we'll look at those now. But I hope you got some intuition as to how QLDPC codes get more efficiency than the surface code. So let's go back to the favorite infinite plane where everything is nice and there's no long-range boundaries. And let's draw a check very similar to what we just saw. There's one last bit of tooling that I want to equip you with. It's something that I was very confused by, but it's actually very, very simple. It's called the stabilizer polynomial. That is just jargon for how do we describe this shape? How do we describe this red tile with the 2 sort of long-range checks? And to do that, we need to sort of take note of the lattice that we're actually drawing. It's actually 2 sublattices. Maybe someone already noticed that. let me just highlight one half of the lattice. These points, they all lie on a perfect grid. And these yellow points, they lie on another grid. These grids, I can't draw sort of lines, straight lines through all of the qubits, but I can if I sort of divide it up into these two sublattices. Now this is just mathematical help so that we can describe the location, the coordinates of these stabilizers, of these checks. We need to describe the coordinates on both lattices, just a detail. And the way you do it is you can define an origin. We'll choose that data qubit over there. You can choose whatever. It's just labeling a qubit. And then you have a polynomial. The reason why it's a polynomial, that won't matter for us too much today. There are some technical reasons behind it, but for us, it's a very simple coordinate or a way, a map of how to draw your stabilizer. That's all that this is. X means you're taking a step to the right. So x to the power of 1 means one step to the right of the origin. Y to the power of 1 means you're taking one step down from the origin. And xy to the power of 0 means you're at the origin. And so by including these monomials here into your polynomial, you're saying that on the blue lattice, these are the data qubits that belong to my check. Does that make sense? It's just really the rules of the game. And then on the yellow, we can define another origin, and we can build up a very similar polynomial. It looks complicated at first, but really it's child's play. It's just describing how to start at your origin and then include the data qubits that belong to your check. And then you have these two polynomials corresponding to the blue and the yellow data qubits. And together, they tell you what the shape of your stabilizer is. This is a tool. You'll see it all over literature. But now looking at it, you know what it means. You know that a higher number here means I'm going further away from my origin. You know, as a designer, that means you'll have to design a long-range coupler. Let's give you another example. Here, you have, this check is only touching 2 blue qubits, so there's only 2 blue terms, but there's 4 yellow terms. Makes sense, one step to the right, another one, and one step down. This one here, that's actually the stabilizer that was demonstrated in practice, so let's introduce it. It has this shape, 1 plus y to the 1 and x to the 2, and kind of flipped on the other lattice. So these polynomials, that's the last sort of tool we need. That's how you describe long range or these non-local parity checks or parity checks in general. This is a common language used to describe the structure of codes.
From online, are active QEC codes that are partially hardware agnostic beneficial for certain sizes of processors? How might we be able to achieve fully hardware agnostic passive QEC codes for larger problems?
Don't know if I understand exactly what it means. What I do want to say is hardware agnosticity or being hardware agnostic is something that's kind of not immediately possible. With error correction, it's very much tightly interlocked with the hardware. The connectivity that you need to build is what the designer needs to implement. But once you've built a layer of like surface codes, you're basically taking your superconducting circuit hardware and now you're thinking about it as a layer of surface codes. And then you're maybe more hardware agnostic already. So if you're taking those logical qubits and pretending they're independent qubits and you can put them into another code, maybe that outer layer of code is a hardware agnostic code. That's maybe my best answer. There's also something about passive error correction in there, but if we can talk offline or after the presentation if that's more pressing. All right. Now to get the IBM code, the bivariate bicycle code, the BB code, there's a simple rule of how to actually get that from a polynomial. So you have this polynomial, it's describing the shape of your check. You're already scratching your head because you don't want to build these long-range couplers. The way you get the Z check in the bivariate bicycle code is by taking the transpose of those exact same polynomials. Let me explain you the name. Why is it called bivariate bicycle? Maybe someone of you asked themselves that already in the past. I did. Bivariate, that just means X and Y. Bi variables, there's 2 variables. Basically means you're embedding this on a 2D plane. So that's why it's called bivariate. Why is it bicycle? Well, it refers to the symmetry in this code. The code has transpose symmetry. You get one basis by transposing the check on the other basis, just like the spokes in the wheel of a bicycle are symmetric with respect to transpose. So that's why it's called bivariate bicycle. It's basically referring to how the code is constructed. And the last thing, now we have both the X check and the Z check. You know what we do in the infinite plane. we just tile the lattice. We just move the checks all around, and that will dictate how the code is constructed. So let's move this one to the right. Move this one also to the right. Again, we need to check that commutation is preserved, but the checks overlap at 2 points, so that's okay. If we move the code up, they still overlap on 2 qubits. And basically, you get at the intuition very quickly that because of that transpose symmetry, commutation is preserved regardless of where the stabilizers are overlapping. What does this mean for connectivity? What does that mean for devices? That's what this means. Not great. This is the Z-check. And now we'll do the same thing. We'll tile the lattice. And you'll see something quite scary happening. Right? Okay. Can we do one more? What I want to draw your attention to is the base lattice is actually a surface code lattice. It's a nearest neighbor lattice. So we know maybe how to do that. But on top of that, now you have these long-range couplers that connect every check qubit to 2 distant data qubits. And we're just tiling the entire plane using these checks. So I've only drawn a small subset of what fits in here. But this is kind of the idea you start getting of what IBM wants to build. So again, on the infinite plane, you reveal the bulk connectivity of this code. It's nearest neighbor. It has wait for coupling. But on top of that, you have 2 long-range checks. And again, same game. We put this on a torus to get a finite size. It's just connecting the left boundary to the right and the top to the bottom. But it gives you a donut. And then you can tile sort of the surface using these long-range checks. And this will introduce some even crazier periodic boundary connectivity. But already in this case, the bulk connectivity has some long-range coupling. And I really want to say both the surface code and the QLDPC code existed in this torus. So being in a torus, that's not really a property of QLDPC codes. Periodic boundaries, that's nothing special. The surface code has that. What really matters is the bulk connectivity. If you're in the infinite plane, do you have long-range checks or no? That's what matters. So being on a torus and having periodic boundary checks, that's an artifact of trying to embed this infinite plane in a finite space. That's important to know as a designer. Is what you really care about are these bulk long-range couplers. So let's go to a concrete example in literature. IBM proposed this in 2023, got published on Nature, front page 2024, massive result. This is a code that has the parameters 144, 12, 12. So 12 logical qubits at distance 12 takes 144 data qubits to build. That's 288 physical qubits because you also have check qubits. Mind you, this is just theory. They didn't do this in experiments. I want to give you, show you that you actually now possess the ability to understand what's going on here. The checks are the ones we've been looking at, just that these long-range checks, they're a bit further away. They're in sort of the bottom left and the top right, and it's transposed for the Z check. I'm just going to flash the polynomial really quickly. They choose like origins that are a bit more offset. They're free to do that. It's just a mathematical kind of choice. And then you have Y1 and Y2, and you also have X3 for your blue lattice belonging to the X check, and something similar for the yellow lattice. And so these polynomials describe this connectivity. So now, when you see this, you at least know what that means. You know the connectivity in the bulk. You know that you tile that around a torus. In this case, they also suggest a toroidal embedding by drawing these arrows. This means the left is connected to the right and the top is to the bottom. And I want to show you that this is actually quite cool, the knowledge we've gained, because they give us a list of a table. It's a list of codes. And before I knew about this polynomial stabilizer, I had no idea what was going on here. But now we actually know what this is. This is really just describing the shape of the checks. And the order of the polynomial, that kind of tells you how far you're going from the origin. So what does that tell you about x to the 26? It means you're going 26 data qubits away. This is a very, very long-range coupler. All of a sudden, you're looking at this list that you thought is reserved for theorists. But as a designer, I know I want to stay away from this part at the bottom. And I'm looking at this here, and maybe these polynomials, they look kind of OK. They look maybe better, at least. Oh, yeah.
So I just want to kind of ask, here we got fixed A and B for different kind of surface physical setup.
Mhm.
I'm just curious how you determine that specific, like transformation or shuttling. Is there any constraint that so push you to that kind of thing?
So your question is how do we come up with these polynomials? Like, why do we choose these? So the answer is they actually sort of numerically just searched for different polynomials, and then they calculated the NKD. And they then they filtered through the list of the best NKD with the most forgiving polynomials. So they were just like really going through all possible stabilizer tiles. You define A and B. You know how you get the other check, it's just transposing these. So all you need to define is these here. And then they just calculated what came out and plotted the best candidates over here, really. Yeah. Exactly. Yeah. Yeah. This is the bivariate bicycle. But yeah, essentially, this is what they did. Also, I want to draw your attention to, if you look at these two polynomials and you count the number of monomials, we could count 6, right? So that means that every qubit is connected to 6 other qubits. So that's another thing. The two things you can get from this is, what's the weight of my check? Every check has, is made up of both A and B. So every check has 6 connections, and the distance of that check is sort of roughly the order of the monomial. So that's what you can get out of this table. Yeah. Yeah. Yeah, that's a good question. It's not been studied a lot yet. We assume uniform error rates. The code threshold, assuming a uniform error model for the bivariate bicycle code, is roughly the same as the surface code. It's slightly higher even. So it means that you can run this code if you have like a physical error rate of 10 to the minus 2 to 10 to the minus 3. That's when you can start thinking about it. But in practice, the long-range couplers might be worse. I mean, depending on the numbers. From IBM, I've actually been seeing good numbers, but I don't know if that scales as favorably. Yeah, you might have to do simulations on that, and it could be an interesting avenue for theorists to look into.
Yeah. I just touched on this, and I'm sorry if I missed it. But why do the exponents of the polynomial for the one with 360 data qubits, why are they so much larger than the exponents for the one with 750? I guess I just assumed that it would scale with the number.
Yeah. It's a good question. I mean, it's not entirely clear how this polynomial leads to that NKD, but this is a good segue to what I want to show over here. You can use this NKD, you can create a metric called the logical efficiency. It's like sort of the goodness or the performance of each code. K, the number of logical qubits, we want that. D is also the distance of the code, also something good, we want that to be high. And N is the number of physical qubits or data qubits required to build it. And so in the surface code, you can trust me, the parameters are n1 and square root n. So putting that in, you get a logical efficiency of 1. Kind of neat that the surface code pops out to be 1. It's like a reference. And now to your question, if we look at this list of codes that I've sort of redrawn over here and look at their logical efficiency, you can see how their score fares against the surface code. Essentially, this factor that you can see is essentially the factor by how much fewer qubits, physical qubits, you need to build the same number of logical qubits compared to the surface code. And so you're getting factors of 6, 7, 13, or even 20, 25 in these different bivariate bicycle codes. But why do these numbers behave exactly like that? I guess so far it's only been studied numerically, and they've just been trying out different stabilizer shapes, and this is sort of what popped out. This is the list of highest performing codes that they found, but there's no inherent underlying story that they've uncovered yet as to why these shapes lead to that specific performance. But still, you can see that using longer range coupler, and that's sort of the point that I want to draw here, draw your attention to, is that the more longer range the coupling, the more efficient sort of these bivariate bicycle codes. Yeah.
How is the hardness of the decoding compared to?
There is, that's a good question too. Decoding, again, is you look at the syndromes, the error checks that light up on your check qubits, and you try to infer the error location. And you can use algorithms for that, heuristic algorithms. For the surface code, we use minimum weight perfect matching or union blossom, union find. I don't know. There's many different algorithms. For LDPC codes, it's a bit less studied, but there is one called belief propagation ordered statistics decoder. It works very well. It's quite competitive with the surface code decoders. The only problem is it's not really suitable yet for real-time implementation, so that's something people are working on. But yeah, the decoding problem is hard, but it's, I'd say, comparable to the surface code. Yeah. And believe it or not, that hot mess we just saw was actually built and put onto the archive last week by a Chinese group. If you would have shown me the connectivity and told me you want to build it in 2D. I mean, this is flip chip, but they're doing all their crossings in 2D with just air bridges. I should have, I would have thought you're crazy and said that you don't deserve any funding. But they did it, and they disproved sort of what I was thinking. And they specifically built an 1844 and an 1863 code. So that's 4 and 6 logical qubits. This is the polynomials. As you can see, it's kind of lightweight. It's not too long range, but still impressive that they did it. 18 data qubits, 14 check qubits, 84 couplers, both short and long. Everything's tunable. And they resolve the crossings with air bridges. So their designers thought, we're up to the challenge. We can do it. And they did it. So we won't get into too much detail, but go ahead and check out the paper. Super cool. It kind of feeds in directly to what we talked about today. They also have a great theory section that goes in a bit more detail than what I did into how you get these polynomials and build up the code. But still, questions remain. Can you cut up this torus? I mean, it's a torus. We cut up the surface code. Maybe we can do the same over here. Can we also rotate the lattice to maybe increase the efficiency and reduce the number of physical qubits? All of this will have implications for the device architecture, and we know how to ask these questions now. Okay, so I realize we're already at time. I want to ask, should I stop here and wrap up, or can I go five more minutes? Is that okay? Okay. So device architecture, kind of the climax of what this is all building up to. You can see that building this here is actually a subset of the connectivity required for what the Chinese group did. You might not want to do it in a 2D way, right? Long term, we might have to have better ways to resolve those crossings. They said in the paper there's a lot of crosstalk they measured. And so one way to do this in superconducting circuits is using multiple layers. Now, we had an amazing talk today morning by Ben, who talked about how they do this at Rigetti, using both flip chip and TSV technology. Quick recap on what that is. So you have control and readout circuitry coming in somehow on one chip, and then there's a second chip that you can bump bond onto this carrier using these green, typically indium bump bonds that glue and connect your chips together. But now, if you want to sort of route and connect them up, if this was just a service code, we can do all the connections on this layer, right? There's no crossings. It's all great. But if we want to resolve some crossings, you might want to sort of break out to a higher layer. And for that, you have to dig through the chip. Essentially, you build these sort of vertical tunnels through silicon vias. You can route a coupler through it, so it's metallized on the inside. And then you can route across on the top chip and route back down. That might not be enough, so you might want to repeat this and repeat it again. And then you can call me crazy. But this is what we can do to get more flexibility in laying out and embedding these codes. You can kind of see where this is going. This sort of Donkey Kong style routing essentially is reminiscent of the VLSI problem, the problem of embedding large connectivity graphs in classical electronics. They also have multiple layers, and they use complicated optimization algorithms to find the best layout, and then they build that. For us, it's more challenging. We need coherence, we need superconductivity. But in principle, there's no reason why we can't at least try to move in this direction. And so taking that same large code that IBM proposed, we routed it using a small homegrown optimization algorithm. And so the base layer looks like a surface code, but then the top layers are a bit more messy. But in principle, with like 3 routing layers, you could embed this complicated code on a superconducting qubit device. If you're like the group that demonstrated the BB code, you might try it in 2D. But this is potentially the more scalable approach using 3D integration technology that people are building towards. And so you can actually summarize the cost or the complexity of building such a device in a number of metrics, like the layers, the number of bump bonds, the number of TSVs, the length of the coupler. Put that all in like some weighted sum and create a cost. This is a bit arbitrary, but I just want to draw the point that we can estimate the cost of building any such code and have a hardware complexity scale here. And then we can plot all the different codes. We can lay out a bunch of different codes and measure their cost, right? And maybe we'll add a second axis, which is the logical efficiency, sort of the performance of the code. How efficiently is it encoding protected quantum information? And so the surface code is, like you expect, would be somewhere in the bottom left. It's not encoding a lot of qubits, but it's also quite easy to build. So it's in the bottom left of this hardware complexity axis. But then if you go here, plot some different codes, the BB codes from IBM, you kind of see exactly what you expect. You're moving to the right because you're making the codes more efficient. But as you're moving to the right, the codes get more complicated and the hardware complexity goes up. So this is data we found numerically using our homegrown optimization algorithm and then just measuring and estimating this cost numerically. And then there's some other codes that you can study, and you can see that they're more towards this region. That is actually the region we want to move towards. Yeah, it's actually covering this up, but this region on the bottom, that's really where you want to be. These are codes that are easy to implement because they're on the bottom and they're very, very efficient. So we want to find and discover more codes that are in this region. And so for theorists, if you're a theorist working on quantum error correction, know that we can build multi-layer architectures. At least we plan to maybe in the future. The hardware complexity depends on a number of things, but what we want is a QEC code with a high logical efficiency and a low hardware complexity.
Are these all these references that collecting or any hardware?
So this is embedding these codes onto multi-layer architecture for superconducting qubits. Yeah. So this plot would look very different for different hardware modalities, but maybe we need a plot like this for every hardware modality, and we pick the code that's on the bottom right. Right. So that brings me to the end. Let me just skip to the final slide. This is the last slide, I promise. For designers, what does this all mean for us? We've taken a week of or 3 days of designing, and we now learned about what error correction has in store for us. On the qubit coupler level, we need long-range couplers if we want to build efficient codes. Bulk connectivity is what really matters. There, the range is sort of mid-range, you know, x to the something. But the long-range boundary, from putting it in a torus, that's kind of annoying because those are the longest range couplers, and they're not really the ones that contribute to the power of the code. But still, you might want to build that. I mean, IBM is trying to build that. These long-range couplers need to be tunable. How do we get the control for the couplers to them if they're tunable? High-weight coupling. We need qubits that can do more than weight 4. You can think about what the implications are for qubits. Do you use floating transmons that support maybe slightly higher capacitive budgets? Do you use grounded transmons? What about fluxonium? Fluxonium is known to be notoriously hard to couple more qubits to a fluxonium than in transmons. Weight 4 is already kind of scratching the limit. Can we really go to weight 6? Or how do we do that? If you're looking for a good research project, maybe there's one. Higher weight coupling for fluxonium. How do we, do we embed the connectivity for one code in a static way, or is there some routing that we use? There's people working on quantum routers where you can have switchable links, and maybe that can give you more flexibility in embedding a complicated connectivity. And on the device fabrication level, for all fab people, we need multi-layer stacking of chips to get routing on of couplers on higher layers. We want bump bonding between these layers, TSVs through them. How do we shield the qubits from coupling to higher layers? Right? How do we reduce crosstalk in that scenario? And yeah, we touched on TSVs already, but we need to be able to move long-range couplers not just X, Y, but also in the Z direction. We go up using TSVs. We need to route couplers maybe through bump bonds. Are they high quality enough? Or can we also resolve crossings using flip chip air bridges like we saw in Ben's talk today? So these are all questions for us to take home, things for us to chew on and to sort of think about as we're pursuing research. But that's all I have for you today. I'll take any questions. Thank you. That's a very good question. Yeah. So what we looked at today is, can we pack more logical qubits into the same number of physical qubits, right? That's what LDPC gives us. What you can already imagine is that if you're squishing all these logical qubits on the same tight space, operating on them individually gets significantly harder. For logical computation, I mean, getting computational capabilities in LDPC codes is a very active field of research right now. There isn't a metric like that, but maybe there should be. But the notion is there that you shouldn't just look at the logical efficiency. That's just half the story. Really, computation is what you need. I want to say that people are now, especially IBM theorists, are now really having some really good breakthroughs, pushing the boundary on what's possible. At least in theory, they found a way to efficiently add slightly more data qubits, actually on the order of d. D is the distance of the code, to do computation. But now you're adding more qubits to your code. You're adding couplers into the code, so the connectivity, explodes even further. But in principle, there's an answer. You can do it, and there's an answer for how you can do it. But it is still one that requires work to make more practical.